I am very thankful to be here at the Groundwater Summit. It's my first Groundwater Summit that's not online, so this is great. My name is Micaela Pedrazas. I am a hydrogeologist working with LRE Water, and I'm very excited to present on groundwater data analysis and visualization as a path to better understand and communicate the status of our aquifers. I'm super excited about this breakout session, especially just looking at the tools that we have to really help GCDs make data-driven decisions. I'm going to start out by going to the heart of the matter, which is why we need data analysis and visualization in the first place, how we can apply it to the kinds of water data we work with, and how to center our tools and apps on the end user. I'm going to show you a practical example of us doing this with the Clearwater Underground Conservation District with their Aquifer status tool. And I'll share a couple of ideas for some future efforts we have in regards to that tool. All right, so if you guys were in attendance yesterday, in the morning session, we heard that data is key, right? So that's awesome. We know that data is key. So the first and most important step before we can do any analysis to try and understand what's going on underneath our feet in our aquifers is really the data collection. We need reliable, accurate, complete, and accessible records that GCDs should have the responsibility to maintain and to be able to keep. So what kinds of data are we expecting from the districts? We have some well construction data. So that includes any data from borehole stratigraphy. And this is just one of my fieldwork glam shots 10 days ago. I was supervising a well rig there. So we took borehole stratigraphy measurement every 10 feet, and we were trying to characterize how much sand or silt there was every 10 feet. So that's important information that we should always keep whenever we're drilling a new well. We also have casing data. Where is our aquifer screened? We have well monitoring data. So we monitor water levels for our aquifers, and we monitor water quality from groundwater samples. Now, we know that water levels are a fundamental indicator of the health of our aquifers, and they especially give us an insight on what's going on with our aquifers through time. So we're really able to see how our aquifer is changing and how it responds to different hydrologic stresses. For example, how does my aquifer respond to pumping nearby, or how does it respond to droughts? Water quality helps us be alert of any emerging water quality issues with our water, and whether it's being compliant with our drinking water standards. We also have geologic models like Michelle Sutherland just presented, and we are able to, well, this is one that we actually made from geophysical peaks in our study area, but we're able to really integrate that data set to what we already know and where our well locations are, where we may not have someone in the field logging the stratigraphy every 10 feet like I was, and we're able to simulate and understand what is most likely our geology going to be near our wells. And finally, we have groundwater models, right? And that's great because the board puts a lot of effort in order to build the groundwater availability models in the state of Texas. So we understand the regional groundwater flow, and we're also able to understand simulated water levels at our well locations because we have access to that information. And finally, there's regulations to add on to the list. So it's clear that the districts face a grand challenge, balancing the needs of the public, which is the people they serve, meeting regulations, and the conservation and protection of our aquifers using the best available science. Now, if I were to go ahead and say, okay, I have water level data, how are we going to use this to help inform decisions? How are we going to visualize this? A first step might be to do a scatter plot such as that one, and maybe run a linear trend curve and say, okay, well, that's what the water level decline rate is looking like. Well, next month, I'm gonna get new water level measurements in the field, and I need to update that chart And it doesn't give me any information on how it compares to the simulated water levels from groundwater models in the area, or any information about where the well is located, how close is it to the faults. So we see that we might have to pick and choose which data sets we want to present, or we may try and compare a couple, but it seems like an effort has to be made in order to integrate all these data sets. And this is what LRE set out to do with Clearwater, in order to be able to integrate all these different data sets to be able to gain a more holistic picture of what's going on in our aquifers. To build a tool like this, the first step is to actively listen to the district. And I mean, that's what our first priority should be as hydrogeologists. So we work hand in hand in order to really convey a narrative of what's going on in our aquifers with the most up-to-date data. We then define a shared or common goal or purpose for the tool. And the question I like to ask myself is, how is this tool or app going to help inform decision-making? Or how is it going to support decisions? Because if your tool is not really helping inform decisions, then what good is it? In our case, the tool is really, the main purpose is to help evaluate DFCs and compare it to our measured data. The next 3 steps are to brainstorm solutions, to build and test them, while incorporating the feedback of the district. So this tool dates back to 2014. It started out as an Excel sheet with water level measurements. By 2016, it was written in R programming and had a web-based interaction. In 2018, the prior consultants developed the alpha version, which included some user-friendly elements, so the user is able to explore the data a little bit more. And finally, I came along in 2020 to help develop the beta version, which included some enhancements in order to bring it to the place it's now. So something that I wanted to note on this approach, which is focused on the user, is that it's an iterative approach. It's a loop that continues to feed itself. So as the district changes and their needs and wants change, so does our tool. We're not going to develop a tool and leave it outdated, and maybe that's not going to be applicable in the next 5 years. So the 2 main goals of the Aquifer Status tool are to improve the understanding of aquifer dynamics and to improve the evaluation of the status of the desired future conditions. Within the first goal, we're really trying to bridge the gap between science and the public. So we want to give the user the tools to be able to access the most up-to-date data that's out there for the district, to be able to explore it, to ask their own questions and build their own hypotheses using the most available, most recent measured and modeled data. We want to be able to let the user graphically and interactively see all of the data that's available by saving them the step of having to dig through hundreds of Excel sheets and trying to put the data together, and if there's new data, trying to find out where it is. So having everything centralized in one place. The second goal of improving the evaluation of the DFCs is something that has been talked about a lot yesterday. One of the questions that was asked was, well, how do we measure if we exceed the DFCs or are we going to meet them, right? And the answer was, well, we need to develop some analytical tools, and those tools have to be reproducible, standardized, and we need to have it recorded. So we came up with 2 different tools to evaluate the status of the DFCs. Essentially, as you can see in that table, for each aquifer in the district, the Upper Trinity, Middle, and the Lower Trinity, we have adopted DFCs values. Those are the current ones. And for the DFC period, which is 60 years. Using those values, I just divided the adopted DFCs by the number of years, which is 60 years. We can calculate an annual DFC, which would give us information on, okay, how are water levels changing through time annually, such that I would meet the DFC or maybe not. And we compare those values, which are based on groundwater models, to field data. So actually water levels that have been measured in the district. We do that using 2 methods, the well analysis and the spatial analysis. So the first method is the well analysis. We have the border of the district or Bell County right there. And just for sake of simplicity, to explain the methodology, I'm only going to include 6 wells. So let's say we only have 6 wells in the Lower Trinity Aquifer. If we try to understand what's going on with the water levels in our aquifer, well, we need to look at where we're measuring those water levels. So let's focus on one well, in this case, the Peerage City of Temple number 3. We can open up the tool, which this is how it looks like. When we navigate to the sidebar menu, we go to well analysis, scroll down to the Lower Trinity well analysis. And what you're seeing here is first the selection of your well. So that's a drop-down menu. It has all of the wells that are most up-to-date on the database. And then you're able to choose your well. In this case, let's choose the Peerage City of Temple number 3. So all the data got updated. Right now, what you're seeing in the bottom right, the casing diagram, where we have the recent geological model data extracted at the well location. So we know essentially what stratigraphy, what formations the well drilled through, and where it's been screened. With that same y-axis, which is depth, we have the hydrograph. The hydrograph is plotting all the water level measurements collected through time. And in this case, we're seeing it from 1952 all the way to 2021, which is the period of record. And we have a best fit line running through those water levels. We can change the period of record to the DFC period. So let's see what those water levels look like between 2010 and 2070. So we just toggle that button, and we see that now we see that linear trend and where we actually have our data. So one of the cool things about this tool is that it's going to be able to extract simulated water levels to compare from all the groundwater models we have in the database. So in this case, I could add those into our plots. If we look at the water level trend, we see that the slope, which is automatically calculated in the fast statistics row, is about a 4 feet decline in the water levels per year. We can include the groundwater models by toggling the measured and modeled button on. And we can see how the current water level decline rates compared to the modeled ones for the DFC period. There's 4 lines there because there's 2 groundwater models in the area, and there's 2 of them have been adjusted by consultants through Clearwater. So we have the 2 different ones and the trend adjusted ones. All right, so the tool was able to give us, calculate that water level trend for one well. We're able to download the data for that well as a CSV to make it accessible and transparent for the users. And we're also able to download that hydrograph to then share it with board members or the users or whoever. All right, so that's the Peerage City of Temple number 3. It's about 4 feet per year water level decline. The tool can calculate it for all of the wells in the Lower Trinity Aquifer. In this case, we're only using those 6 wells. And in order to understand what's going on an aquifer hull basis, we can calculate an average of those slopes to give us an average aquifer water level trend. We can do a similar analysis using the medians. And we can compare those to what the annual DFC trend is, which in this case is negative 5.5 feet per year. As you can see, both our average and median aquifer water level trends are suggesting that we might meet the DFC if we continue at this pace, since it's declining at a slower rate than what the DFC indicates. So that's good. Now let's do the same analysis with all the wells that are currently in the Lower Trinity. And again, the Lower Trinity seems like it's going to meet the DFC based on the available data. These results are going to be summarized in the dashboard of the tool, which is essentially just the DFC tab, and then you click on the DFC results. In the DFC summary for well analysis, the first 3 columns are what we've mentioned, just the annual DFC calculation. Then you compare the average and the median current trends for each aquifer to the DFC annual values, and you're going to have a current status. If it's declining at a slower rate than the DFC, and you might meet it, it's going to be colored in green. And if it looks like it's declining at a faster rate, it's going to be colored in red. So that's one method. What's the limitation with the well analysis method? Well, as you can see, the wells are not evenly or regularly distributed throughout the district. They tend to be located where pumping is happening, and that's a fact. We drill in a biased manner because it results in best economics, so we don't have enough data points where pumping is not really occurring. So one way to address this is through the spatial analysis, which is essentially an interpolation throughout the entire county of using those well points. Now, in this case, we're doing interpolation to create annual gridded data. So for every year, we're going to have an estimate of what the water elevation surface looks like. That's the water elevation. We have the contour lines that are colored in green on top of our dark blue lines. And the user is able to control the contour interval, which year, which raster the user would like to see, and as well as what map type, whether you want to map the water elevation, or sometimes it's useful to map the water levels. In this case, I'm going to change the contour interval from 50 to 80, and we see that my contour intervals have changed here. So there's some user buttons that are very handy because it allows us to do our own exploration. So what we did with these rasters is we subtracted them from the 2010 initial DFC period water levels, such that we could see what the difference is from that initial value throughout the years. And we created this plot, this scatter plot. It's automatically created with the tool. And you can also calculate a slope of that line, or the water level decline rate. In this case, it's negative 1.8. So it's a lower or slower rate than what we calculated with the well analysis. Again, we compare it to the annual DFC water level trend, and we see that this analysis will also indicate that we might meet the DFC. One of the great things about this tool is that if we have the data set for an aquifer that maybe we're not evaluating the DFCs, but we have the data, we're able to use the same tools to just explore how that aquifer is doing. In this case, we're looking at the Edwards Aquifer, where we know that we don't have a DFC right now. But that's the Edwards Aquifer. It doesn't cover the entire county, which is why you're only seeing a portion of it. That's the water elevation map. And right now, it's only showing the contour intervals, and it's showing the well locations. With this information, we would be able to see the groundwater flow direction. We can also add springs. So it's a little bit hard to see on the screen, but I just added some spring locations in a cyan color. And we can also include the fault data, which is information we get from like Michelle Sutherland, in order to be able to get all the information from the consultants we worked with and put it all in one place for the user to explore, okay, what's going on in that well that's really close to this fault, or what's going on close to springs, right? So there's the dashboard again, and it's a similar results table as the well analysis. We just compare the average and median current trends to the DFC annual trends, and it tells us whether the status is declining at a slower or faster rate than the DFC. The last tab I wanted to talk about is the water quality, which is something that we should always be keeping track of and monitoring, and there's a lot of effort that's being done to monitor, especially the Edwards wells around. In this case, I'm looking at the Edwards water quality, and this plot shows it for one well, which is the Avila well, but it's giving you all the water quality measurements that have been taken for the well. In this case, there's 3 water level measurements in a time series. I'm plotting all of them, but the tool lets you plot whichever water quality parameter you want against another tool in order to create some cross-correlation plots and to understand if there is any correlation between water quality parameters. So what are some next steps with this tool? Well, we'd like to incorporate the water usage data into our analysis, so that's reported pumping from users that we'd be able to see and plot or correlate next to the water levels and see if we're seeing something there. We'd like to include the spring flow, especially for the Edgeworth Aquifer, and be able to include that into our database, as well as any rainfall data, precipitation, and see how fast aquifers may be recharging. An education component would be a pretty simple addition, in my view, in order to let the public be involved in the science and be able to toggle around the tool. We want to incorporate error and uncertainty statistics, since we do use groundwater models and geological models that carry uncertainty with it. Allow real-time updates to the database. Currently, we need to download an Excel with all the data to upload it to the tool, but in a few months, we're hoping it's going to be just a very seamless addition. Obviously, we'd like to make it mobile-friendly so that we could do it just from the field using cellular data. And as always, we're just trying to tease out new questions with the data and let the data speak for itself rather than forcing the data to tell us a story. So, although this may seem like a small step in the data analysis and visualization field, we believe it's a step in the right direction. And we simply wanted to design a tool that could just get quickly to the point, let the user ask his own questions, and help inform decision-making in regards to the DFCs. So thank you for listening, and I'll open the floor to questions. Yes. That is correct. The geological model is from Michelle's and Vince's efforts that we bring in. And whenever that gets updated, they send us the files and we're able to update it on the tool. So then the user can just get the most recent one. Yes. And from the groundwater models, we're just extracting the simulated water levels that we can plot with the water levels. Correct. They continuously work on those faults, and they just send it to us as a shapefile, and it's easy for us to include it to the tool, and you could see it with any of the aquifers. I only showed it with the Edgeworth aquifers, but you can see the fault lines overlaid with any of them. Yes. Yeah, that's a great suggestion, and it is one of the plans is to enhance our water quality tab. And for example, if we had more parameters, we could do a stiff plot. But if there is enough data density, we could be able to build a raster. Yeah, the problem is that there's not a lot of not enough water quality measurements for specific years. But with the Edgeworths, we're seeing that every time there's more and more. So that's a great idea. Awesome. Thank you all for listening, and I'm really thankful to Tag D for being able to really help scientists get together and join our efforts in order to understand our aquifers better. So, thank you.